Good morning. Today we'll be doing an example of molecular orbital theory. Shown here is one example using O2 minus. So on each side of your MO diagram will be the atomic orbital. On one side we're gonna put the oxygen minus here. So normally the valence of oxygen is 6 electrons. So we're gonna put that 6 electron on the right hand side. And because we have an extra electron, we're going to go ahead and put that O minus with 7 electron on the left hand side. Now it doesn't matter if I switch these two around or not, they'll be the same. Now we're going to go ahead and fill up our atomic orbital, and it's going to be 7 electrons on this side and 6 electrons on this side. And in the center, we're going to have our MO diagram. So we're going to go ahead and drop that in, allocate your electrons into the different level. So we're going to start with the sigma bonding orbital. 2 electrons goes into there. Next, we're going to add into our anti-bonding orbital, also sigma star. And now we're going to move into a 2p level. Be sure to not to mix the 2s and the 2p here. And count the number of electrons that you have on the 2p and make sure that you add in the correct amount into your MO diagram. So we're going to go ahead and add our electrons from the 2p, from the atomic orbital into our molecular orbital. So I'm going to add into the sigma 2p bonds, and notice that I put them with parallel spins according to Hund's rule. So we're going to keep on adding electrons. The next 2 sets of electrons are with opposite spin according to Pauli exclusions rule. So I'm going to go ahead, we're going to start with the pi, move into the sigma bonding orbital, and then now we're going to get into the anti-bonding, and I believe we should have a few more electrons to add in, maybe 3 more. So we're going to add 1, 2, and 3, and this will account for all the electrons that we have. So now the question is, what bond order do we have with O2 minus? Now, normally O2 has 2 bond order. So how about this particular case? So the way we figure out the bond order is by 1/2 divided by the number of bonding electrons minus the anti-bonding electrons. So in this case, let's start counting the number of bonding. 1, 2, 3, 4, 5, 6, 7, 8. So we got 8 bonding electrons minus the anti-bonding. So anti-bonding is one with the star. So we got sigma star 2 here, and then we're going to have our pi star and 3. So we're going to have a total of 5 anti-bonding electrons. So if you do the math, 8 minus 3 gives you 3. 8 minus 5 gives you 3. Divided by 2 will give you 1.5 bond order. Now, normally oxygen 2 has a bond order of 2. So this tells you that the bond order for our example here has weaker bond energy than the normal O2. And also, likewise, since the bond is weaker, the bond length is longer than your normally standard O2. Now, the next question is, what kind of magnetic property does it have? Is it paramagnetic or is it diamagnetic? And the way you could tell is by looking if there's any unpaired electrons or not. So if there's an unpaired electron, then it's paramagnetic, meaning that it is magnetic. So in this case, we have 1 unpaired electron, making this a paramagnetic compound. So our next example is F2 2 minus. So normally fluorine has a valence electron of 7, and in this case we have 2 extra electrons. So we're going to go ahead and put 1 extra electron on each of the individual fluoride groups, I mean. So now on this F minus, we'll have 8 electrons on the right hand side, and we're going to have F minus on the left hand side. So 8 electrons here, 8 electrons here. We're going to go ahead and fill it up from the valence of 2s to the valence of 2p. Now that we have all our valence electrons from the individual fluorine groups, fluorine, keep confusing that. Fluoride groups, we're going to go ahead and drop in our electrons from the atomic orbital into the molecular orbital in between. And we have our patterns here where it's sigma, sigma star, pi, sigma, pi star, and sigma star. Go ahead and allocate your electrons into the MO diagram. Drop it in, start from the bottom and fill it up to the top. And fill them up with opposite spins. So we're done with our 2s level. We're going to go ahead and move into our 2p orbital. Put them in parallel spin in the beginning, followed by opposite spin. Okay, so we finished filling up our bonding orbital. We're going to move into our anti-bonding. And I believe that we should have 6 more electrons to fill in. So we have a total of 12 here. Keep that in mind. And we fill in 6. We got another 6 more to fill. 2 here with parallel spin. And then we're going to add 2 more with opposite spins. And then finally, we're going to put 1 and a second one on top. So as you can see, we've completely filled in our molecular orbital diagram. Now the question is F2 2- a stable compound or not? The way you can tell if it's stable or not is by looking at the bond order. So let's go ahead and calculate that bond order. And as you recall, the bond order is simply 1/2 times the difference between the number of bonding electron minus the anti-bonding. So let's go ahead and calculate how many bonding electrons we have. So the bonding one is without the star. So 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bonding electron minus the number of anti-bonding. The anti-bonding is the one with the higher level with the star on it. So how many anti-bonding electrons do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. So we get 8 minus 8 divided by 2. And that gives you a bond order of 0. So what does that mean? It means that since there's no bond order, this compound, it would not be stable and would not normally be found naturally in nature, versus F2, which is very stable. And so if we have F2 2-, it's an unstable compound and it normally would not be found. And thank you for your time, guys.